Welcome to the first of this two-video series on air and air pollution. I'm Aida Awad from Broward College. The learning targets for this video will be to describe the characteristics of the troposphere and the stratosphere. We'll also touch on the mesosphere and the thermosphere. To illustrate the Coriolis effect on global atmospheric belts, and to explain the generation and movement of air masses. So we're going to start off with a little bit of a case study here. Something called global distillation effect, or perhaps the grasshopper effect. This is where we've observed toxic compounds that are found far from the regions where those chemicals were originally produced and entered the atmosphere. And the general movement is from lower, warmer latitudes toward colder, higher latitudes. And the reason that we know these chemicals have moved is that we find them in people that live in those higher latitudes and in animals that live in those higher latitudes. And they concentrate in the body fat of those people and those animals. So you can see a little diagram here showing that the less volatile air pollutants are moving up towards the mid-latitude range, and the more volatile pollutants move actually all the way up towards the northern latitudes. Some evidence that we have of this is concentration of these organic pesticides from both Inuit mother's milk and polar bear mother's milk. And you can see PCBs, chloridanes, chlorobenzene, HCHs, and DDTs in this diagram are predominant. So that's a problem that should lead us to thinking more about what do we know about the atmosphere. And let's start with the basic composition of the atmosphere. First of all, that thin blue line of the atmosphere that becomes less dense as it extends out into space is composed of just a few chemicals in large percentages. The atmosphere is 78% nitrogen, 21% oxygen, and then the minor components, carbon dioxide, argon, other gases, and even water vapor are in small amounts. And you can see in these boxes here the relative proportions of each of those major compositional elements of the atmosphere. The atmosphere provides several ecosystem services, including shielding the Earth from some ultraviolet rays, being a greenhouse gas trap that traps heat, which we often hear in the media is a bad thing, but actually it's necessary. If we didn't have the atmosphere to trap some heat near the surface, the Earth wouldn't sustain life. Layers of the atmosphere. What we're most familiar with is the layer closest to Earth's surface, and that's the troposphere. It has an average thickness of about 12 kilometers, a little bit thicker at the equator than it is at the poles. And that's the atmosphere that has weather and winds and most of the clouds in it. Now, if you're going on a trip and you're flying in a plane, you might actually reach the top of the troposphere in that plane. You'll notice on the left side of this diagram that the red line indicates the temperature change with increasing height in the atmosphere. So from the ground level, with increasing height in the troposphere, temperature decreases. And again, if you've ever been on a plane and you've seen the readout of the outside temperature, you might notice that it might be 40 or 50 degrees below 0 Fahrenheit, and there you can see exactly that situation. Moving into the stratosphere, you'll notice that temperature actually stays fairly constant initially, and then temperature increases. So it goes back up to almost 0 degrees Fahrenheit. Characteristics of the stratosphere are that it extends up to a height of about 50 kilometers. There is a steady wind that blows in the stratosphere, but it's not a turbulent wind as it is in the troposphere. So if you're taking a flight and it suddenly gets bumpy, pilots might actually go up into the tropospheric level to get away from that turbulence. In this layer, you also find the ozone that absorbs much of the Earth's damaging ultraviolet radiation, and that because of that ozone's presence, the temperature is increasing slightly with increasing altitude. The next layer above the stratosphere is the mesosphere. And again in the mesosphere, you notice that temperature declines rapidly. So the mesosphere extends from about 50 to 80 kilometers above Earth's surface. And in this area, temperatures can be as low as 138 degrees below 0 Celsius. If you ever watch a meteor shower, it's in this layer that the meteors are burning up upon entering Earth's atmosphere. Finally, above the mesosphere is the thermosphere. And it's named the thermosphere because temperature increases very rapidly. And then above the thermosphere is the exosphere. So we're now outside of Earth's atmosphere. In terms of atmospheric circulation, circulation in the atmosphere is dominant because of convection currents. So we think about convection as being heat rising, and that's exactly what's driving this system. It's variations in the solar energy that reach the Earth, so warming up the ground, heating up the air closest to the ground that causes that warm air to start to rise up. And it's this convection process that generates air currents and causes the mixing of warmer and cooler parts of the atmosphere. So you'll notice in the diagram here, those red arrows indicating warm air rising, so a low pressure situation as that warm air rises. It rises up, cools off, and begins to sink, so a higher pressure leg as that air begins to sink down towards the surface. You can see in a more global way the pattern of atmospheric circulation. So starting at the equator, there is a circulation, a convection circulation of trade winds, that warm air rising at the equators and then sinking at about 30 degrees north or south latitude. The westerly winds are generated at about 60 degrees north or south latitude with rising air there, some of which moves to the south back towards the equator in the northern hemisphere and sinks, again at about 30 degrees north. And additional air from the westerlies rising at about 60 degrees north latitude forms the polar easterlies that rise up and then sink around the North Pole. Moving now towards looking at the deflection of those air patterns. So we have what's called the Coriolis effect. One thing to remember is that in the northern hemisphere, air is deflected to the right or in a clockwise direction. And that happens because of what we see here in the top two diagrams. So in the first diagram, you'll notice that the black arrow at the equator indicates the distance from, let's say, the prime meridian over to this line of longitude. To the north or the south, close to the poles, that same black arrow going to that same longitude line is shorter than it is at the equator. Well, since Earth is spinning as a sphere, that must mean that different portions of the sphere are moving at different rates. The black lines are different lengths, and Earth is spinning as a sphere. And because Earth is a sphere, as it rotates at different latitudes, there are different linear speeds. So any object, such as air, that's not tied to the ground will be moving in that circular motion, that clockwise motion in the northern hemisphere or deflecting to the right, counterclockwise motion in the southern hemisphere or deflecting to the left. And that's the Coriolis effect. Okay, I think we're ready to check in on our learning targets. So we described the characteristics of the different layers of the atmosphere, including the troposphere and the stratosphere. We illustrated the Coriolis effect on global atmospheric belts, and we explained the generation and movement of air masses. Go ahead and take your mastery check quiz, and I'll see you in class.